Excited that Peter Geoghegan is here. He's a Postgres contributor. He does a ton of work on the indexing and vacuum parts of internals in Postgres. He has a talk for us today on Bloat. He is going to take questions during the presentation.
There will be multiple opportunities to take questions.
Great. And let's welcome Peter to the stage with a round of applause.
Thank you. So yeah, I'm known for, I think, principally for work on B-tree indexing. A lot of work in recent releases on vacuum too. This could be thought of as my sort of idiosyncratic take on vacuum and bloat. We've heard already who I am, so I should also point out that every slide at the bottom here has a URL, which obviously you can go there even right now, and you'll see the slides for yourself. The intention here is that this talk is kind of a bit of a thinker, perhaps. So my hope is that it will, in some cases at least, be more informative, perhaps on a second viewing or something like that. You know, there's Easter eggs, links, things like that. So that's something to consider. So getting started. So I'm taking, as I mentioned, my own sort of idiosyncratic skew. That's how I'm going to go through the subject matter today. I'm sort of taking what I'm calling more of a bottom-up approach, where I'm starting with the physical data structures themselves, and only later linking that to the vacuum process, the way in which we address the problem. This isn't necessarily the best way to go about it. What I'm sort of trying to do more than anything else is to give you a framework, a mental model upon which to, let's say, hang other stuff that you already know from other places, other practical experiences you might have with the same sort of general subject matter. So this is not maybe necessarily the best way, and certainly not the only way of going about discussing this material. I can recommend, there's a talk next door, a little later on, from Chelsea Dole. The talk is more sort of user-orientated and is more concerned with how things are affected within the application, as opposed to this talk, which does touch on things like that a little bit, but it's more a case of how the application affects vacuum. So it's more the other direction. Let's get started. Okay, so I'm going to first talk about structure of access methods themselves. That is, how at a very high level, things like the heap table access method, the standard way in which the system stores items in tables, and also the way that the system stores items in indexes, how they are addressed at a high level. I'm going to start with that as a sort of a build-up to the main kind of meat of the discussion. So, what is a taxonomy? Well, a taxonomy is, yes, sir. Okay, so this mic is a little problematic. I can't really, because it keeps falling. Sorry. Remind me if I'm doing a bad job of that, if you don't mind. Tell me if I need to do that, if I need to adjust it again, because it's hard to monitor. So taxonomy in general isn't. Okay, this is just not working. Excuse me. How's that? That might be better. Hello. Okay, that's better. If it's turned on, it might be better. How's that? Hello? No. Testing. Okay, better. Thank you. Okay, so in general, a taxonomy isn't, you know, it is a framework for discussing things. The definitions are justified by the fact that it makes it easier to discuss things. So they're not the absolute literal truth necessarily. all models are wrong, some are useful. So with that in mind, I'm sort of presenting in a sort of an abstract way how the access methods are sort of addressed, how they work at a high level before relating that to Bloat. There is a sort of tension between logical and physical in these things. If you were dealing with a system like InnoDB, say, that uses a clustered index, an index organized table, quite naturally, the records in the table are addressed using primary key value, both externally and even internally. So, for example, the purge daemon from MySQL's InnoDB storage system deletes entries from secondary indexes by looking them up by key value. So it's a pure logical, purely logical approach in terms of how entries are addressed. In contrast, Postgres takes what's sometimes called a physiological approach, meaning that entries in tables have a TID, tuple ID, so it has two components. It is a physiological identifier because it has a physical block number, shown here in red, and a logical page offset number, shown in green. So we need these things to be stable in order that we can avoid breaking index scans. We also, so it's a nice compromise because it's kind of a hybrid approach between pure logical and pure physical, because the byte offset where the actual physical tuple exists within the page that can change, and change quite a lot actually, because in any case we're accessing it through the indirection of the page level offset number. So we can access physical blocks using a physical offset number, so we can immediately jump to whatever block we need. But then within the page, since it's effectively a logical page offset number, we're not bound to. We can, for example, fragment the page at will without that breaking queries. So it's a good compromise between a purely logical approach, such as the InnoDB one I'd mentioned, and another. There are also purely physical approaches that can work, such as MyISAM in MySQL. That also has downsides, though. So it's a good kind of combination of the two. Indexes, of course, are more like indexes even in Postgres are indeed addressed by looking stuff up in the obvious intuitive way. It's a tree structure. That's just how it works. There's no stability or indeed any need for it in the same way there is for the heap. Heap access methods have to have a stable TID in order that the things that are pointing into the table, i.e. the indexes, don't break. So there are important requirements around the stability for an extended period of time. We need to know that those things are going to be consistent, so there needs to be strict guarantees there. So this is, I think, mostly something that this is more of an advanced talk, so I assume that this is mostly something that you'd already have pretty good idea about. It only works in that direction. So vacuum in Postgres will never do what I described purge InnoDB doing, where it will look stuff up in the secondary index in order to remove it using the same logical identifier as queries used to look up stuff in secondary indexes. Rather, the bulk deletions that take place in vacuum for a variety of reasons are just using the physical TID. So by its very nature, vacuum is a bulk operation that has to do a linear scan of the indexes. It's not incremental at all. So it would be convenient, perhaps in some ways, if it was able to do something a bit more like the InnoDB purge thing. It doesn't. So it's an inherently bulk operation. So this will become more important later on. I'm contrasting this with other techniques that are not so monolithic, not so top-down. We're building up to that. These are opportunistic techniques. So InnoDB purge is not opportunistic in the sense that it's equivalent to vacuum more or less at a high level, whereas opportunistic techniques run within queries as they execute. They are incremental on demand. Often this is not at all apparent to you as a user. Often it is just something that's happening all the time, continually without your realizing it. Unfortunately, the instrumentation of this stuff is not as good as it really should be. But so it's not at all obvious that this is happening in many cases when it is in fact happening and is helping you to a great degree. Okay, so I'm going to move on to the sort of main portion here, this bottom-up take on bloat. This is a picture here this is a generic image of a cell from biology. If some of you might remember from high school biology, it's possible to say a great deal about a cell without specifying what greater whole it's a part of. That is, is it a part of there's a great deal of difference between a skin cell and, I don't know, a liver cell or something like that. They obviously do have significant differences, but nevertheless there is a great deal of commonality between them. They have a shared structure. And I think that that's an interesting metaphor for how pages work in a system such as Postgres. We can say a great deal about pages without specifying what kind of page it actually is, and indeed the high-level structure, while very important and relevant, can actually be ignored when discussing this stuff. We can have a very useful conversation without necessarily specifying which larger structure we're talking about. So that's really the idea I'm sort of driving at here. You have something called the page model. It's kind of a very sort of it's something that we sort of hoist atomic operations, complicated atomic operations. Transactions are essentially composed of simpler lower-level ones that operate usually on the level of individual pages, occasionally one or two or three pages. So we can sort of hoist complicated atomic operations, transactions from these smaller ones. And the reason why I like to discuss this is because it's kind of hard to remember. There's always so many details with all this stuff, too many for you to remember even if you're an expert, but you can sometimes, it's sometimes much easier to remember stuff if you remember the relationships between them, because then if you sort of think about it for a little while, you might realize, well, there's only kind of one way it could work, so obviously that's, there are consequences if you remember the sort of important rules, and it kind of falls into place. You can sort of rebuild how it must really work in your head without having to remember all the details, so that's kind of what I'm driving at here. There's so much that could potentially be relevant. I think you need maybe a bit of a shortcut if you really want to go deep. There's also a sense, I think, in which these things have kind of evolved. These things are so complicated that there's only so many things that could work. So, again, it can be very informative, instructive to think of the relationships between the things if we really want to go deep with this stuff. So, with that in mind, here's a picture of a page in Postgres using a tool that I kind of wrote. It's doing those annotations for you. It's actually a page from it's called PG hex edit. This is a page from a heap page from a system catalog. So the way this actually works is you see these arrows here. This is a pristine page. So everything is in order already. in other words, there's, within this page, things could be randomly shuffled. They're not right now. But for a variety of reasons, things get shuffled. And the indexes that we're pointing to these things at the top here, these are called, things at the top are called item identifiers, the blue things. So that's a fixed-sized array at the top there. So the page offset number is logical in the sense that it references one of those item identifiers, and there's an additional indirection, an offset pointing to a specific tuple, which is the structures down here. So that's kind of what's going on there. The indirection is an idea that we apply in many different ways all the time, and it's kind of encompasses a great deal. Continuing, this is an index page which is on the same, as it happens, on the same table. A lot of commonality here. The same page layout. The tuples are a bit different, but actually even they share a lot. So again, we have this low-level view of things, which is we've surprisingly similar structures here, even though at a high level we are completely different things. This extends to bloat too. Bloat tends to look kind of similar if you look at it at the page level, but if you reason about it from the sort of vacuum high-level point of view, it's kind of different, and we'll see why in a minute. You know, there are various cleanup techniques that apply equally, or that there are variants. You know, you've got something called heap pruning, which can take place opportunistically, and you likewise have opportunistic index deletion, which both work by cleaning up extra unneeded versions on demand in passing as queries execute. Opportunistic means that the queries sort of understand, okay, you know, I see a bunch of extra versions here, these are superfluous, good time to get rid of them, I'll just do that, I'll zap them right away. So because this is happening without it being particularly well instrumented, it may be happening all the time without you realizing it. And here we see it's actually the same sort of thing again. Here, these red item pointers these are dead item identifiers in the heap. There's like I said, I'm not going to show you an example from the index, but suffice it to say that it is very similar. Again, but in both cases you have versions of the same logical row. The same row itself will tend to accumulate 1 or 2 or 3 or 4 dead versions together, so they're right beside each other. So it's convenient for these opportunistic techniques to sort of target concentrations of bloat from particular logical rows. Does anyone have any questions on any of that so far? I don't know if I like Chelsea, yes. Yes, so the question is, is the order preserved by appending stuff to the end of the page, or is it ever possible to, it's actually a great question, is it possible to do something else that doesn't, that allows you to sort of reuse some of the, so that kind of is anticipating what I'm going to talk about, so I must be doing a good job. It's only possible to reuse the things in the heap structure, the dead item identifiers, when we know for sure, when we guaranteed, we don't just have a good idea, we know for sure that nothing is pointing to them that could get confused. So we can free those tuples, and we can, in the heap pages, through pruning, and we can just leave these stubs. These are like tombstones. But what we cannot do is we cannot reuse them completely. Now, on the other hand, vacuum, as we'll see, will sometimes be able to make these, in its what we'll see what I'm going to call its third phase, it'll be able to mark them as reusable. And at that point, they can indeed be reused, but only when they're marked reusable. So that dead goes to reusable, and then it's safe, because Vacuum will do that only when it knows that there can no be any dangling references, since we don't want wrong answers to queries, right? We don't want index scans to sort of find that, oh, the TID that they imagined was pointing to whatever's in the index, it's pointing to some completely unrelated thing. That would be disastrous. That would be terrible. So at no point can that be allowed to happen. So anyways, as I sort of referenced earlier, this idea that Vacuum is sort of top down, and the structure of the index access methods at a high level, the fact that we have these dependencies, these high-level dependencies, are much more important with Vacuum. So Vacuum is good because it puts a floor under everything. I'm just going to... Vacuum serves to make sure that we at least get to every page that might have any bloat in it at some reasonable kind of frequency. So we have this sort of floor to everything. But it doesn't understand, if you like, that some pages are very different to other pages. Some pages have vastly different requirements. If you update, the best way to predict what row is going to be updated in general is to look at the recent past. The row that's most likely to be updated, generally speaking, is those that have been updated in the recent past. That's a pretty robust heuristic, at least. So probably most individual pages of the database at any given time have practically no risk of that happening. The chances of it happening are very low. But then there will be some where there'll be dramatic skew. So in many ways, we need these opportunistic techniques in order to sort of allow Vacuum to act as if these distinctions don't exist. Vacuum is totally naive about these things. So Vacuum is following some fixed rules. It has some very limited ability to do things like drop some work, but for the most part, it's following fixed rules. It has a fixed processing order. What I'm saying are sort of three basic steps. Fortunately, these days, the instrumentation of Vacuum is a lot better, so you can actually see this for yourself relatively easily. We'll have examples of that. So the first step, as I put it here, is there's an initial heap scan. And that's the process through which Vacuum, which itself does pruning, will access every page that has any chance of having any dead tuples. Some can be skipped using something called the visibility map. Now at that point, some of these can be removed immediately, those that are heap-only tuples, which I describe in a minute. Others will have these dead item identifiers left in place. These are the ones that will need to go remove from indexes. This is where the dependency I'm sort of keep going on about becomes important. The second step is where we actually go to all the indexes, each and every one of them, no matter what, and we remove any of those index tuples that have TIDs that point to the stuff that we need to get rid of generally. Now, because we have all these opportunistic techniques, it might be that there's relatively few in each index. It might be that there's a lot of them in one index in particular, and other indexes that happen to be able to use those opportunistic techniques to good effect will have much less of a problem, and therefore will have far fewer things to delete. It's complicated, but there's a great deal of natural variation, if you like. And then finally, there's a third step where we go back to those pages, not all the pages that we visited, but those that we either pruned and created dead item identifiers that we collected in a list, or those that we at least found a pre-existing one because they can be left behind from before, the dead item identifiers. The TIDs point to dead item identifiers. There's an array of TIDs. We delete those from the indexes in the second step, and the third step, we go back to the heap pages themselves, and then we make those dead item identifiers reusable, so it's safe to reuse them then. So you were asking before, Chelsea, about, so once that happens, then we can reuse them. But we can't, because of that stability thing being essential here, we can't do anything that's going to confuse things, because of course indexes are sort of operating from a great distance. There's so many things that could be pointing to something. We really need this sort of clean sweep to manage the dependency. We could do a great deal elsewhere. We'll see more about that. But overall, we need this sort of clean sweep thing within Vacuum. And Vacuum is the only thing that'll do this third step here, because there's nothing else that has the kind of high-level context sufficient to make sure this is going to be safe to reuse these, to make these dead item identifiers reusable. There's going to be a sort of an example of this that will hopefully make it a little clearer that you can run for yourself. So again, Vacuum itself is uniquely capable of this, making these dead identifiers reusable, because only it can make sure that there couldn't possibly be anything in indexes pointing to these things that we're now going. Only it can make it safe. Here I'm going to show a worked example, very simple example. This is a vacuum verbose here. So we're creating a table, we're inserting some rows into it, and we're deleting 1/5 of those rows. And so we're using this option index cleanup off, which is effectively making vacuum skip the second and third step as I describe them. So we see there's 200 tuples removed. It's probably a little difficult to see that from it. Like I said, the slides are available there, but what it's saying there is that you have these 200 dead identifiers that remain in the table, and it says the index scan has been bypassed. So this option is sometimes used in emergency situations and stuff like that with freezing, but it's mostly a developer option at this stage. So this is basically just a way of saying, just give me the first phase, which you probably would never want to do, but it happens to be an easy way of explaining the material, so that's why I'm using it. Now, what you could subsequently do immediately afterwards is you could do another vacuum, and I've explicitly asked for index cleanup on, but you could just omit that completely. And now you're seeing there's 0 tuples removed, because we already removed the tuples. But it'll do an index scan, it'll do the second step, and it'll say there are 200 dead item identifiers, not tuples, dead item identifiers, that it removes from the table in this sort of third step. So we've sort of, by initially doing a vacuum with the index cleanup off and then doing a regular vacuum immediately afterwards, we could see how the details changed. It's finishing off the job we started in the first manual vacuum operation, basically. So that illustrates the point quite well, because you can see, hey, there's a difference between a dead tuple and a dead item identifier, and sometimes it actually matters a lot. We have these things called hot updates, where if an index isn't updated at all, we can have 2 different versions of the same row living side by side on the same heap page, where they don't have any. Heap-only tuple literally means only the heap structure has a tuple. So there still is something pointing to the root item of the hot chain within each and every index, but it's not pointing to the successor versions. There's an additional indirection. So you go to the root of the hot chain, and then through that you go to the heap-only tuple. So because it's only pointing to the original TID, there's nothing to break. Of course, this could only work if it just so happens that your updates don't change any column. It's kind of an all or nothing thing, in the sense that it doesn't matter if it's only one indexed column. If you've got 10 indexes, each and every index will require successor version. This is traditionally kind of the Achilles heel of hot. There's also a way in which hot can be very good with opportunistic pruning, because you can completely have a very stable, within a page you can have very stable reuse of space, because exactly, if you're updating, say, the same one row again and again, then you will systematically free space from older versions and then reuse that for newer versions again and again, and in a certain sense completely be freed from any dependency on vacuum. That would be the ideal case. It's often not possible. But what we do have when it isn't possible, which sort of is in more recent versions, Postgres 14 in particular, we have better opportunistic index deletion, which complements this sort of stuff in the heap in particular. It used to be that, so even if we don't have hot updates, we can still do pruning opportunistically. The only downside of that, the only way in which it's not as good as when we just have hot updates, is that we're going to accumulate these dead item identifiers. But those are like 4 bytes, whereas the tuples themselves are certainly at least 32 bytes and maybe hundreds of bytes more like. So it's not ideal, but like we can afford to store a lot of those relatively small 4-byte dead item identifiers. We can sort of hold the line for vacuum. Vacuum will eventually get to those, but we can at least be traditionally, even before 14, the heap page itself wouldn't maintain quite its pristine structure, but it would sort of hold itself together reasonably well, even if we couldn't use the hot optimization. The problem was indexes would accumulate versions, but in 14 that got a lot better. Indexes in 14 are more intelligent about cleaning up version churn, where you have sort of the same thing of the same logical row being updated again and again, and getting concentrations of bloat in a relatively few, usually a relatively few index leaf pages. So it's sort of, when hot doesn't apply and you've got like 10, 15 indexes, it's ideal there because it won't be particularly effective on that one index that you did change, but all of the other indexes will, generally speaking, have their original pristine on-disk size preserved. So that's a big improvement in practical terms. But of course, you have to be on Postgres 14 to avail of that. So again, vacuum, top-down, works at the level of the whole table and its indexes collectively, in contrast with these sort of what I'm calling bottom-up techniques. So there's a kind of a complementary relationship here, a sort of a yin-yang thing, where they sort of have different strengths and weaknesses, and they naturally they go well together, let's say. Another way of looking at this, another example I think encapsulates what I really mean here. If you think about it, deleting 1 million rows once versus deleting 1 row 1 million times, theoretically these are kind of the same thing, or very close to it. But I think in a practical setting they're usually not. And what I mean by that is, so opportunistic techniques are good because you reuse the same space very quickly, very incrementally, on demand. It matters where the space is, what the space is used for, and where it comes from. Like you want to be reusing space locally for related versions if it's updates, and even to some extent if it's deletes. Whereas with a bulk deletion, with one big delete, you kind of just have a bunch of free space that's generic free space at that point. I'm not saying that there's a very clear delineation here, but I think it's pretty clear that if you contrast those two extremes, they are really quite different. And that difference, I think, is a good way of thinking about the sort of top-down, bottom-up dichotomy. That's maybe the example that sells it best. Okay, now I'm going to talk about vacuum's priorities. So before I start on that, I'm going to take any questions, because because you should ask questions. If you got any, I encourage it. It's yes. I'm sorry. The question was, what are the caveats about running vacuum too often, or? Well, it's designed to be non-disruptive. Actually, this is what I'm just about to talk about. It's designed to be non-disruptive on the live running system. So theoretically, it shouldn't be too bad. Obviously, there are many details that could matter, but in principle, the design prioritizes being non-disruptive. So it's not going to block, certainly not going to block anything except there might be relation level locks that could block a create index, but your live production workload, your inserts, your updates, your deletes are not going to be affected in any way. So sometimes you'd have problems with things like dropping an index, that blocking vacuum, but even then, auto vacuum can usually, although not always, cancel itself because it understands that, oh, you know, it's not the end of the world if I get canceled, but if I prevent this create index from proceeding, it will itself block other things, so there'll be like a traffic jam. We don't want that, so it'll cancel itself. Usually when you have problems is when all of these things, for whatever reason, don't quite work, and then that becomes very much a question of what you specifically were doing at that specific time, which is hard to make a general sort of statement about. It's supposed to be non-disruptive. Sometimes it's useful if you could do stuff off hours, just because you can, to do it that way. Overall, you shouldn't need to, generally speaking. It should be sufficient to just configure auto vacuum in a way that isn't too disruptive and keeps things going. The important thing is that, like I said, vacuum puts a floor under everything. It makes sure that something, at least, runs that does clean up. It might be that the opportunistic stuff is doing a great deal of the heavy lifting, but at some point it needs to run too. It also should be said that because all this opportunistic stuff has gotten a lot better, particularly in 14, and then you've got index deduplication and stuff like that, that has tended to make vacuum run a lot more nicely, just because its share of the burden, if you like, has been lessened by things working a lot better elsewhere. It should be noted that, like, in extreme cases, those techniques are vastly more effective now. That could make a huge difference. Does that answer your question? Is that sort of okay? So getting on to the thing about vacuum's priorities and its non-priorities. So it's all about being non-disruptive. It'll sort of throttle itself. The worst case query response time, it's all about the worst case with vacuum, right? Because, like I said, vacuum is going to run at some point, so therefore, even if we make very pessimistic assumptions, we can still have relative confidence in the worst case not being too bad. There is some sense in which reclaiming space is also potentially important, but overall it doesn't tend to be the main priority. So we have this sort of implicit assumption that things are more or less getting reused. It's not the assumption. The implicit assumption is that space will get around to reusing it when we get around to reusing it, and for the most part that is true. If you have a bulk deletion or something like that, you really do want to reuse that space pretty eagerly, though, and that's where vacuum is or could be very important. There are rules around how the space can be reused both in the heap structure itself, in addition to index structures. Fortunately, the instrumentation of this stuff in auto vacuum has gotten a lot better. I'll show you some of that in a minute. There are rules about in index access methods as well. You can reuse pages. You can recycle them, but they have to be completely empty. So there are sometimes problems with things like sparse deletion patterns. Whereas if you've got a bulk deletion, you're usually going to be able to free a significant number of index pages too. One thing that I find interesting and I think has real practical relevance is table size, or vacuum operation size, I should say, perhaps. How big tables and small tables, theoretically there's no reason why they should be very different, but in practical settings they tend to be kind of different. I mean, the rules are the same, but the consequences of the rules are maybe not. So, as a general rule, the larger the table, the less frequent the vacuum operations, the bigger the vacuum operations. And there can be sometimes a kind of too big to fail dynamic. The example I might give is how I was saying earlier about auto vacuum cancellations, how that's really no big deal with a very small table or even a medium-sized table because, okay, it got cancelled, it'll restart again. You can afford to have something go wrong if you're having these all the time. The frequency and the size, the frequency of these operations relative to everything else is high. Whereas you could have these sorts of very large vacuum operations on a very large table infrequently, and then you kind of get squeezed if something goes wrong. The problems compound in a way that could be much more problematic. So I'm going to show you an example that I think makes the point in a minute. So one way of dealing with this is table partitioning. It's very simple because then the partitioning children are effectively independent targets for vacuum purposes. So it's a very simple way that you could ameliorate this kind of thing. It was probably a good idea anyway, so if that's at all possible, that's one strategy that can work rather well. So this is going to work best if you have data that's naturally amenable to that, but if you don't, you might want to look into more frequent vacuums through auto vacuuming. This becomes tricky because if you are too aggressive about it, that could be very inefficient because you'll effectively be, depending on workload characteristics, much depends on workload characteristics, you might be sort of revisiting the same pages that are getting updated again and again and not doing terribly much of any use each time, and yet paying a rather high cost for it. So we don't want to do that. And whether or not we're doing that may well depend on workload characteristics. Here's an example. This is from a benchmark from TPCC. You have this big append-only table that has lots of updates, and it keeps growing and growing. So it's a big table, getting bigger all the time. Fortunately, the instrumentation of this stuff is a lot better, especially in Postgres 14 and now 15 and now 16. So here we see, highlighted there, the number of pages scanned. That means the number of pages actually, heap pages that we physically did anything with at all, that we touched, which you'll notice, of course, so there's about 72% of pages were skipped in this one example, because the visibility map was effective. Because once this particular benchmark does updates, but once it updates every row in this table once, and then it's done forever with those rows. They'll just age out. So it's kind of not an append only, but it's a mixture of append only and update once, basically. So the visibility map is pretty effective here. So if we increase the frequency of vacuuming, suppose we double it, ideally the number of pages scanned would halve. That would be a little optimistic, mind you, but we might ideally hope for that. So in that ideal world, we're not paying an efficiency cost by having more frequent vacuums. We're not sort of wasting our time spinning our wheels, processing the same pages again and again to little benefit. So you would want to look for the number of pages scanned being stable or even going down as you increase the vacuum frequency. That's something to look out for. Another thing to note here, there's an optimization that we see is used here, where there's a very, very small number of heap pages that have dead item identifiers. On that basis, the vacuum will say, you know what, I'm not going to scan all these indexes just to remove what is, by any standard, a very inconsequential number of index tuples. I'll leave it till the next time. Because this is just a long-running vacuum, in red here we see there's so many dead but not yet removable tuples, because vacuum deletes things that were garbage at the start of the vacuum operation, and it doesn't worry about things that became garbage as vacuum continued to run. So there's no long-running transaction here, and nevertheless we see, just by virtue of the fact this is a long-running vacuum, it's taking about 9 minutes, I think. There's nothing holding back the horizon that we can use for cleaning up stuff, but nevertheless, just because it takes a long time relative to everything else, it's kind of already falling behind. And this is where some of the danger comes from, this sort of too big to fail dynamic, as I like to put it. Just big vacuums are kind of different to little vacuums. Yes? Well, you could, but I think what you'd effectively be doing at that point is you'd be doing 2 vacuums, right? And maybe that would be great, but that's more of like an auto vacuum scheduling issue. You know what I'm saying? Like, the table is actually growing this whole time, so we're not even going to look at, let alone do anything with those newly appended pages. So things, the world hasn't stood still while vacuum ran, which is good because we wouldn't want it to. That would be very disruptive. But it's bad because, hey, are we already falling behind? So we want, the cadence is important here, right? It's very useful sometimes to look at an individual problematic table and look at a succession of these sorts of things and understand the sequence and understand how, by taking various kinds of intervention, we might be able to do better. It helps a lot that you can skip indexes now, because it used to be that if there was even one thing that you had to delete from any index, which is silly, very inefficient. Now, at least, if there's not too many, then we won't completely waste our time. So that's one way in which it would be more practical to increase the cadence at which auto vacuum is running with that kind of thing in mind. But of course, we still have to make sure that it's not, you're not getting very little benefit out of it as you continue to make it incrementally more aggressive or run more frequently. Okay, so some conclusions here. Just sort of summing it up. Any other questions? Mr. Arbitrate. Yeah, I deliberately ignored that. I probably should have. That's a good point. I've deliberately put that to one side. Oh, incidentally, I did a bunch of work on freezing in Postgres 16, which will make it more reasonable for me to ignore these things and pretend that you don't have to worry about bloat, even though that's probably not true. In other words, it is more proactive about freezing, which is how we maintain transaction status information. The intention in this work and in other work is that you can sort of pretend that that's something that isn't directly relevant to you, that gets taken care of in passing. I don't think we're quite there yet, but I have ignored that because I think the system should allow you as the user to ignore it. It's kind of weird the way it works. So yeah, that's my idiosyncratic. I probably should have been a lot clearer on that, so well spotted. Anyone else? Okay. Now, some conclusions. Vacuum is tasked with removing old garbage. Well, we all know this. Recent Postgres versions do much better. Even it wasn't until Postgres 15 that you could even see the scanned pages thing I was showing you, even though it's very basic information, which is, I don't know. So that's getting better all the time. It's worth being aware of, at least, the fact that these opportunistic techniques are likely running for you all the time and doing a great deal of the heavy lifting. And moreover, are acting in concert with vacuum itself, which is constrained by being this sort of top-down, inflexible maintenance process. You can't tell too much about how this opportunistic stuff is what it's doing for you, but you can kind of infer it. Like, if you notice that there's hardly any tuples removed in the auto vacuum log or vacuum verbose, but you do see a bunch of dead item identifiers that got there somehow. You didn't do pruning that put them there, but somebody did. Stands to reason that those were from opportunistic operations, which could indeed be, like I said, doing a great deal of the heavy lifting for you. There's this kind of complementary relationship. I've called it a yin-yang. Because one is very fast, very local, understands the immediate needs of queries at the level of one page. The other, of course, is thinking of things at the level of the table, and its indexes collectively. So the complementary relationship is something that it constricts things to some degree, but it's also a good way of understanding how vacuum works to realize that the pruning is going on all the time. It may be going on in vacuum. Maybe that vacuum's doing a great deal of it, like that bulk deletion example, but often not. And you might have some parts of the table that are very different to other parts of the table. Real tables are like organic. There's a lot of variation. So it's important to at least have some meta awareness of that, to think, well, how might my table be, how might it have interesting characteristics? Like, are there some pages that I'm always updating all the time, and might be worth considering, well, how's that getting cleaned up if you're running a very busy production system? In any case, it might be intellectually interesting to understand how these things fit together. I think that's all I got. Of course, I will take any questions if there are anyone got any. Okay. I guess not. So I'll just thank you and leave it at that. Thanks.